Hello friends. In our previous lectures, we have been considering different forms of mechanical condition. We have been attempting to quantify these different forms of mechanical condition. We have been attempting to attribute a name to it. We have been attempting to quantify it. And also we have been trying to understand the response offered by these different mechanical conditions. Now all the mechanical conditions that we have considered thus far can be largely categorized into two, that is tensile or compressive loading condition, and the other one which we looked into in the previous two lectures is the shear loading condition. So what we were able to do is we were able to quantify these mechanical conditions, these tensile or compressive loading, and also we were able to quantify the shear loading. We were able to quantify it in such a way that it is independent of the dimensions of the sample. So we were able to express these mechanical conditions and we were able to describe it in such a way that the behavior of the material is also independent of the dimensions of the sample. So the mechanical condition experienced by the material is also independent of its dimension, and the response offered by the material is also independent of its dimensions. So both behavior and the response we were able to describe independent of the dimensions of the sample. Now in addition to that, we were able to relate, considering we have been exclusively focusing on the elastic region of the mechanical behavior of the material. What we have been able to do is we have been able to relate this mechanical condition to the corresponding response, and we were able to identify the proportionality constant that relates the mechanical condition to the response within the elastic region. And this we refer to as the modulus. So we have a distinct Young's modulus that is associated with tensile or compressive loading, and we have a distinct shear modulus that is associated with the shear loading condition. In the previous lecture, we were able to relate or establish a relation between the Young's modulus and the shear modulus. Now this is what we have been doing thus far. Now when you look closely at the different mechanical condition that we have considered so far, for instance, if you look closely at the tensile mechanical condition or tensile loading condition that we have considered thus far, we have considered different forms or different variants of the tensile loading condition. We began with a uniaxial tensile loading, and from that we moved on to a biaxial tensile loading, and finally we moved on to a triaxial tensile loading. So started with uniaxial, biaxial and triaxial. So even within the framework of the tensile loading, we were able to consider three different variants of it. Now what is rather characteristic about these mechanical conditions, particularly one like the triaxial tensile loading condition, is that these loading directions are rather conveniently arranged for us to place it in a coordinate system. Let me repeat, these mechanical conditions that we have considered, even the most convoluted one of the triaxial loading condition that we have considered, the loading directions are so conveniently arranged that they overlap with a definite coordinate system. So if you consider a coordinate system such as x, y and z, in triaxial loading condition, the loading direction that we have considered, they definitely overlap with these coordinate systems. So it is rather easy for us to describe these different directions of loading in a triaxial tensile loading condition using this coordinate system rather in an easier way, because they overlap with, so this direction here overlap with the x-axis, while this direction here it overlaps with the z-axis, while this direction here it overlaps with the y-axis. So we have placed the direction, we have considered the loading direction in such a way that it is easy for us to overlap, or it is easy for us to understand it in the context of the coordinate system, such a way that it overlaps with the coordinate system itself. Now however, in a real life condition, very rarely we have a case where the loading direction is along the longitudinal axis. The loading direction, it overlaps with a definite coordinate system. Very rarely it occurs in a real life application. So therefore what we have is, we have two different forms of, the loading condition that we have, it can be categorized into two ways. One is, we can consider this form of loading condition as an experimental loading condition, or a laboratory loading condition, or a test condition. So These are a technical term, and this is something that you would often hear even a non-technical discussion. So we often talk about a test condition, meaning the test condition is a pristine condition. So if you are planning to buy an automobile, and whenever you talk about, when you want to know about the mileage of the automobile, they would say that this is the mileage of the automobile in the test condition. So they have tested the automobile in a specific condition, and in that setting you get this amount of, or this mileage you would get. However, in real life, you would know that the test mileage would be considerably larger than what you find in the actual road condition. So the same goes here as well. When we introduce these different forms of loading condition, we talk in the context of the test condition. We talk in the context of an ideal condition. However, in real life, the material experiences, the load that the material experiences, the mechanical condition the material experiences, it is rarely along the test condition. It is rarely along the experimental condition. So we need to have an understanding of what would be the response of the material when the load that you impose, the load the material experiences, is not along the lines of the test condition. It is not along the lines of the experimental condition. It is not similar to or identical to that of the lab condition. So that is what would be the foundation of this lecture and the few subsequent lectures. What essentially we want to do is, having understood the concepts, the fundamental concepts of the tensile and compressive loading, and also along with the shear loading condition, now we want to move away from the testing condition. We want to move away from the experimental condition, and we want to get into the actual real life condition. We want to, at least if not exhaustively, we want to know how it is possible for us to relate our understanding from the laboratory condition to that of the real life. So that is essentially what a role of an engineer is. So as a metallurgical engineer, particularly one who has to do with deal with both lab and the real life condition, an engineer comes into play, and this is where your role would be. You try to understand what is happening in the laboratory setting, and you try to extrapolate it to the real life condition, and that is what we will be doing in this lecture. So that this is the start of such an consideration, such an perspective. Now let us again begin with, instead of starting with the triaxial tensile loading, we will start with a simple uniaxial tensile loading. So when you consider a sample such as this, of course, it is very rarely we find a sample of this form in a real life application. Nevertheless, our focus is now on the mechanical condition. So in case of an experimental setup or in an experimental setting, the uniaxial loading condition will be of this form. Now when you consider a real life, an equivalent real life case, it is not necessary that the loading direction is along the x-axis. It can be inclined. So it can be inclined in this manner. So while the black axis, it represents the test condition, the red one, it represents what is the actual direction along which this sample that we are considering, it is about to experience load in the application. So let me repeat. The black, it represents how you test the sample in a laboratory setting, and the red one is the actual loading direction in a given application. Okay, so I hope you are able to make that difference. Now what we essentially know is, we are able to quantify both the mechanical condition that the sample experiences and also the response offered by the sample under the test condition. For uniaxial case, biaxial case, triaxial case, we are now in a position to describe the mechanical condition that the sample experiences under the test condition. So therefore, if we want to know what is the mechanical condition the material experiences under an actual condition, all we need to do is express this in terms of this. Let me repeat. What we have done is, so far we were able to understand both the mechanical condition that we impose on the mechanical condition the sample experiences, and also the response offered by the sample under test condition. Now we are moving away into the actual condition. And the actual condition is different from the test condition. Now when we want to describe an actual condition, the mechanical condition or the stress experienced by the material, the load experienced by the material in an actual condition, if you want to describe it, all we need to do is we need to describe it based on what we already know or what we have already studied, that is based on the test condition. So if we are able to relate the actual condition to the test condition, then the way of describing the material, be it the mechanical condition that we impose or the response offered by the material, becomes easier, because now it is possible for us to describe everything in terms of the test condition. Now with that understanding, let's get into this lecture. So what now we have is, we have the load that we impose, the nature of the load is the same. It is uniaxial tensile loading. So, but what is the key difference is that the inclination here in the test condition, the loading direction is along the x-axis, but in case of the actual condition, the loading direction is rather inclined. Now, in order to handle such a loading condition, we need to develop a coordinate system such as this. So, in order to understand such a loading condition, in order to even describe such a loading condition quantitatively, we need to have a coordinate system such as this. So now we have a coordinate system, and this coordinate system, we could use this coordinate system to describe the actual condition. Only when you have a coordinate system, you would be able to describe a condition such as this. One other way of describing such a coordinate system is what we refer to as the frame of reference. So one other way of describing this coordinate system, which helps us to describe the loading condition, the actual loading condition, or which helps us to differentiate the test condition from the actual loading condition, we refer to it as the frame of reference. So frame of reference is nothing but, at least in this context, the frame of reference is nothing but the coordinate system that helps us describe the loading condition that a material experiences in a real world. When the loading condition deviates from the test condition, we need a coordinate system to quantify it, and this coordinate system is also referred to as the frame of reference. Now, we saw that when we want to describe the loading condition that is a material actually experiences, all we need to do is relate it to the test condition that we have studied. Now, when you focus on the test condition, the cross-sectional area that we consider, the area of our interest is this. So often, the area of our interest, it is in this, along this area, or in this area, we describe our stress. What we mean by stress is, one definition of the stress that we gave is the resistance offered by the material to the imposed mechanical condition, and this resistance is often discussed in this terms, along this particular area, along this cross-sectional area. So, in the framework of the test condition, the area of our interest is generally this cross-sectional area, and now we have a loading condition that is inclined to this cross-sectional area. Now what can be done is, this frame of reference, let's say frame of reference is it's not just for, but frame of reference. This frame of reference can be rotated in such a way that the actual loading direction, it inclines itself, or it aligns itself to the test condition. Okay, so what can be done is, this frame of reference can be rotated in such a way that the actual loading direction aligns itself to the testing condition. Now again, since our focus is on the mechanical condition, we will consider the shape of the sample as it is. We will not be aligning the entire sample or realigning the entire sample. All that we will be doing is, we will be considering the change, or we will be realigning the direction of the loading. So when you realign the direction of loading, now the actual loading condition is something similar to what we have dealt with in the previous lecture. Now we have introduced a frame of reference, and by rotating the frame of reference, so all we did is we rotated the frame of reference in such a way that, we rotated this frame of reference in such a way that now the actual loading condition aligns itself to the test direction that we are familiar with. However, when you rotate the loading direction, what also rotates is your area of interest. The area that you have been so far considering, it also rotates. So even though externally, macroscopically, assuming that we are dealing with a sample of infinite size, we have not changed the size of the sample, configuration of the sample, we have kept the rotation of the frame of reference. Whatever happens when you rotate the frame of reference, those things we have kept intact. So what essentially happens is, when you rotate the frame of reference, in order to ensure that the actual loading direction, it fits in with the test loading direction, what happens is, while this frame of reference rotates, the region of our interest, the region that we are familiar with, is also rotated. So essentially now what we have is, we have a condition that in order to describe the actual loading condition, so we have a setup where in order to describe the actual loading condition, we need to understand the stress experienced by inclined plane. So when we are able to describe the stress experienced by the inclined plane, then we will be able to relate it to the, or we will be able to relate it to, or we will be able to describe the actual loading condition. So to recap, what we have done is, we have moved away from the test condition and the actual loading condition. The actual loading condition we have considered as it is an inclined loading condition. So in order to describe this inclined loading condition, we need a frame of reference, and while rotating the frame of reference, we were able to realign the actual loading condition to the test condition. The reason we want to do is because we already know the test condition is already known, this is known, and it will be rather easy for us to express the unknown in terms of the known, and therefore we are aligning ourselves to we are realigning the actual condition or the actual loading direction to that of the test loading direction. When we do that, the area, the cross-sectional area we have so far been considering, along with it also rotates. So don't be rather misled by the similarity in the shape of the overall macroscopic shape of the configuration. This is for our understanding. But when a frame of reference rotates, all the corresponding parameters associated with also rotates. Only then we can be consistent. And therefore, when we rotate the frame of reference to overlay the actual loading condition to the test condition, what we observe is, we observe that the cross-sectional area that we know what is also inclined. Now what we want to do is, we want to describe the stress experienced by this particular cross-sectional area. Now in order to do that, let us rather simplify this particular description here. So this can be simplified in this manner. When you orient yourself in the right direction, you will be able to simplify this sample in this way, where we have these as our region of interest. The region of interest is inclined, so it is inclined in this direction, and there is this loading direction in red. So we have this loading direction, and we have the region of interest that is in green, and this we will refer to as AP. Now what we want to do is, we want to describe the stress experienced by this region of interest AB. Now I hope you understood why we are considering this region of interest AB, because we want to understand the actual loading condition. What is the actual loading condition? And this actual loading condition, through all these activities, to all these frame of reference rotations on all these different steps that we have considered, we end up having a inclined plane. So when you are able to describe the stress experienced by an inclined plane, then ultimately what you will be able to do is, you will be able to describe the mechanical condition that is imposed by an actual loading condition. So when you have an inclined actual loading condition, when you have a system that imposes a inclined load to your sample, then you will be able to consider, or you will be able to describe this mechanical condition when you focus on the inclined plane, the appropriate, the suitable inclined plane. So that is what we have been doing thus far. Now if you refer to this tensile load as P, we could rather state that the stress experienced by AB is nothing but the ratio of the load and area of AB. So we know that the description of the stress, and the stress, if you just consider it mathematically, by heart you know that the stress is nothing but load and the area, and if you adapt the same description, then you could say that the stress, the AB, the region of our interest, the inclined region of our interest experiences is load by area AB. So you could climb that way. However, what key aspect is missing here is that when we describe the load as, or the stress as the ratio of load and cross-sectional area, there was a physical meaning to it, which we also considered even months before. When you consider stress as the ratio of load per unit area, there was a physical meaning attributed to it. That is, this stress is the resistance offered by the cross-sectional area, or stress is the resistance offered by the material for the imposed loading condition. So you are able to understand that the loading condition was along the longitudinal axis. It was rather it's a tensile loading condition. To the expansion, the material should offer a resistance, and this resistance is along the cross-sectional area because it is rather perpendicular. So when you consider the actual cross-sectional area in the test condition, it is rather perpendicular, and therefore we are able to understand that. So you have atoms aligned in this direction, and your load is trying to pull this atom apart, and therefore there is a resistance offered to this condition, and this resistance we are quantifying using stress. So this is rather straightforward for us to understand. But when we use the same description here for an inclined plane, it becomes rather harder for us to get that similar assumption, to get that similar description. We already have an inclined plane. It is not that the atoms are as regularly as arranged when you consider a cross-sectional area of this form here, and in this context we need to make a physical sense, or we need to gain a physical sense for this stress. So therefore it doesn't make much physical understanding. This expression here does not give us much physical understanding because our region of interest is rather inclined. So even though it becomes, we can at least mathematically give this expression here, but it does not make much sense when you consider it from a physical perspective, because there is a physical attribution to what a stress means. The stress is nothing but the resistance offered. But when your plane is inclined, this resistance offered, this description does not make any sense. So therefore, we need to have a description that is consistent. So that's the reason, one of the reasons why we need to have a description that is relatable to the test condition, that is relatable to this condition wherein the area is perpendicular to the loading direction. So we need to describe the stress experienced by AB in such a way that we are able to introduce this physical relevance. So the physical relevance is only possible when your area is perpendicular to the loading direction. If it is not perpendicular to the loading direction, then the resistance offered by the material is not as clear. It is not as, we will not be able to describe it as clearly as we have in case of the stress. So therefore, what can be done is, it is possible for us to introduce or drop a straight line, or possible for us to consider an area, say BC, which is perpendicular to the loading direction. So the key factor here is this new area that we are considering BC, it is perpendicular to the loading direction. So what we have done is, we have our area of interest, and from the area of interest we are considering a point BC, that from the point B we are considering a area, or we are developing an area BC which is perpendicular to the loading direction. So what it essentially means is that this BC here is similar to the area that we are familiar with, that the test area that we have been talking so far. So all that we are doing is, we are following the framework developed here. We are trying to describe the actual condition in terms of the test condition. The actual condition is along AB, and now we are trying to express it in terms of BC, because BC is the test condition that we are familiar with. And in addition to that, the BC gives us a more physical understanding of what is the resistance offered by AB in terms of, because it is the cross-sectional area of your sample. So it serves two purposes. One, we are expressing the unknown in terms of the known. Okay. And the other purpose, it helps us get a physical meaning of the resistance offered by the AB, or the stress experienced by our region of interest AB. So in order to do so, we are considering an area BC that is oriented, or that is pinned at a point which is also associated with the area of our interest. So we are not considering an area randomly here. We are considering an area that is pinned to our region of interest. So that's the reason why we have a BC here. Now, when compared to this BC, the test cross-sectional area, our region of interest, let us assume that it is inclined by an angle theta. So what we essentially have is, we have our inclined plane, our inclined region of interest, we have our test region of interest, that is the test cross-sectional area. When compared to this test cross-section, or this test cross-sectional area, the inclination of our region of interest is by the angle theta. Now, what we essentially have is, we have our theta here, and we have our so we have our theta here, and this angle is 90 degrees. So all that we have now, when you consider geometrically, is a right angle triangle of ABC. So the triangle that we have now is ABC. Now when you consider the cos of this angle theta, so this theta that helps us describe how our region of interest is inclined with respect to the test cross-sectional area. When you consider this cos of this angle theta, this is nothing but rather adjacent by hypotenuse, so therefore BC by AB. So if you look closely at this triangle ABC, you would understand that the cos theta is BC by AB. Now this BC here is the area of cross section. So area of cross section is A, and let us, because the area of cross section is uniform all through the sample, it is independent of the angle of rotation. We can call it, we can have a constant to refer that. So therefore A, and the AB is nothing but the area of our region of interest. So now we can express this area of our region of interest as the ratio of the A, the cross-sectional area, by cos theta. Again, this theta has a significance because theta is, it helps us quantify the inclination of the region of interest. So region of interest. So ROI is region of interest. So FOR is frame of reference, something that we learnt, or I don't know, we considered in this lecture. And ROI is region of interest. So the theta has a significance. So it talks about the inclination of our region of interest, and A is the area of cross section, that is constant, but the area of our interest, so depending on the inclination, the area of our interest varies, but A is the cross sectional area that is perpendicular to the loading direction, so that is constant. That's the reason there is no subscript associated with it. Now what we have ultimately arrived at is an expression for the area of our interest. Now it is possible for us to substitute this area of our interest here, and then what we would end up having is the stress AB experiences is P by A cos theta. So we are substituting area of our interest AB in this expression here, and it is possible for us to write this as P by A cos theta. So this theta, you can bring this up, and ultimately this P by A is nothing but the stress that we have already considered in our test condition. So the stress, the P by A, that is the load, and the cross-sectional area of the sample along the, which is perpendicular to the loading direction. Again, this A is the cross-sectional area of the sample perpendicular to the loading direction. So this is the A is something that we have been considering in all our lectures. So this is the area. This A is what we have been considering all our lectures, and this ratio of P by A, this stress, makes more clear sense to us primarily because we are now able to understand the resistance offered by along this area or perpendicular to this area. This we are able to understand. So this is something that we have already considered in the test condition, and now what we have done is we have expressed the unknown actual condition to the known test condition of the stress perpendicular to the cross-sectional area, and the cos theta, the theta that helps us describe the inclination of the our desired plane. So what we have essentially done is we have considered an actual loading condition, an actual tensile loading condition that is inclined, and we were able to quantify that, or we were able to manipulate the system in such a way that instead of treating the load as inclined, we have a region of interest that is inclined. So what this theta describes is, this theta describes, of course, in our configuration, in our setup that we have considered, it talks about the inclination of our region of interest. However, this inclination of our region of interest is primarily dependent on the loading direction, the actual loading direction. So, depending on what our actual loading direction is, we will be correspondingly rotating the frame of reference, and correspondingly this theta would vary. So even though we have simplified this theta to represent the actual region of our interest or the inclination of our region of interest, but what it essentially means is theta describes the loading direction, the actual loading direction. So in subsequent lectures we will also take that perspective, but nevertheless what you need to understand is this theta in this subjective discussion. It might appear that it is just talking about the inclined, it is used to describe the inclined region of interest. However, when you take a step back, when you consider why we are considering an inclined region of interest, then you would understand that this theta, it describes the angle between the loading direction that we have considered for the test case and the actual loading direction. Because when you rotate the frame of reference by theta, this actual loading direction will coincide with the test loading direction, but correspondingly this plane here, the region of our interest, will get rotated by an angle of theta. So that is what we have here. So even though theta appears to describe the inclination of our region of interest, what it essentially talks about is the actual loading direction. Now coming back to this expression here, now this is the resistance offered by AB to the imposed loading condition. So this is the stress of experienced by the region of interest AB to the imposed loading condition. Now this makes rather a physical sense, because what we can observe is when your sample is when your region of interest is inclined, the resistance offered by this inclined region of interest is a portion of the resistance offered by the region of interest that is perpendicular. So we have two regions of interest, one is perpendicular to the loading direction and the other is inclined to the loading direction. These are two cross-sectional areas. So one is perpendicular, the other is inclined. So if you consider the context within the sample, so you have, this is an ideal one. This is a cross-section area that we consider in a laboratory setting, and this is an inclined one. So you have a test one and this is an inclined one, so actual one. Now the resistance offered by the actual cross-sectional area, the inclined cross-sectional area for uniaxial tensile loading, is just a portion of the resistance offered by the cross-section area that is perpendicular to the loading direction, the cross-section area that we consider in the test condition. So it is just a fraction of it. Now when you consider from this expression, if you consider when your actual loading direction coincides with the test loading direction, that means when theta is 0, in the special case such as this, when your theta is 0, what you ultimately end up having is the loading direction or the stress experienced by our region of interest is equal to, because cos theta or cos 0 is 1. So ultimately in that case, when there is no inclination, when your actual loading direction is along the test direction, then in that case the actual stress is equal to the stress that we are conventionally associated, that we have so far been studying, the stress that we observe in the test condition. So what essentially we have done is we have now been able to express the unknown response of the material, or unknown actual loading condition to the known test condition. So that is what we have been able to describe. Again, the reason I misspoke of the response of material, because this can also be considered as the response of material, because stress is nothing but the resistance offered by the material for the imposed loading condition. So in that way we are now able to describe the resistance offered by any inclined plane within a three-dimensional system to a imposed loading condition. So irrespective of what is the orientation of your loading direction, it becomes possible for us to describe the resistance offered by the area of interest, the resistance offered by the material to this inclined loading direction, and this we are able to do by considering the test condition. And what we essentially observe is the quantitative understanding that we gain from this experience is that when your loading direction is inclined, then you move away from the test loading condition. The resistance offered by the material, the stress experienced by the material is the portion, is a fraction of the stress the material would have otherwise experienced when you have a test loading condition. So when you move away from the test loading condition, when you incline the loading condition away from the test loading condition, the amount of stress that you impose on the material is a fraction of what you would have imposed had you been along the test loading condition. When you incline your loading condition, you are essentially decreasing the stress experienced by the material. Now, so far we have been, when we consider the system, even though we started off with rather so even though we've been describing, or we were able to describe the sample in this manner, and even though we were able to describe the region of our interest, all that we have been doing is we have been considering a region of interest of this form, and we have dropped in order to describe the stress experienced by the region of interest in terms of the known parameter, we have considered another region. So we refer to this as A, B and C, and we have been discussing this part. Now this expression, what it essentially tells us is, this expression tells us when the loading direction is in this way, the stress experienced by AB is this, that is a portion of what this BC experiences. And again, so what essentially then we have is the resistance offered by AB along this direction. It can be quantified in this expression here. So the stress can be referred to as the resistance offered by the cross-sectional area, and the resistance offered by the cross-sectional area is along this direction here. Now it is also possible when your area of interest is rather inclined, what other factor is different when compared to BC. So when you compare AB to that of BC, one is AB is inclined to that of BC, so BC is the one area that we consider during the test condition. When you compare AB to that of BC, of course we have an inclination of theta. This inclination, what the consequence of this inclination is that when you consider the normal to BC, normal that is perpendicular to from BC, this perpendicular, it coincides with the loading direction. Let me repeat, when you compare the BC with respect, compare it with the AB, that is the region of our interest, the normal of BC, it coincides with the normal of the loading direction. However, when you consider the normal of AB, it doesn't really coincide with the normal of the loading direction. So when you consider the region of interest, of course the stress experienced by the inclined region of interest is a fraction of it, in a fraction of what the stress experienced by the cross-sectional area that we have established through this expression here. In addition to that, what other difference we observe is, we see that the normal is also inclined. The normal of this inclined area of interest is inclined, or it is not along the loading direction. So if you consider, for the sake of the geometry, to understand the geometry of the inclination, let us consider a blown up representation of what we have done so far. So if you do that, so this is our inclined region, and the perpendicular or the normal for this inclined region is here. So this would be the normal for the inclined region. Again, being normal, this assumes an angle of 90 degrees. However, our loading direction is this. So this is our loading direction, and we also have to consider in order to express the stress along the inclined region of AB, we have considered this BC. So the dark black line, it indicates the loading direction. We have our BC that represents the normalcy, and AB that represents our, what it essentially represents is this AB here, it represents the region of our interest. Now the angle that we know about is this, that is theta. So this angle we know about. Now we need to understand, if we want to see what is the inclination of this normal with respect to the loading direction. So this is the normal of AB and P is the loading direction. We need to know this angle here. We need to know this angle here in order to describe how much is the normal inclined with reference to the loading direction. So we need to know the angle in green to understand how much is the normal inclined with respect to the loading direction P. So in order to do that, let us consider a few triangles. For instance, if you consider this angle here, it is 90 degree because BC is perpendicular to the loading direction. So this is what, that's the reason why we call this as a test case, because BC, the cross-sectional area, is perpendicular to the loading direction. So when it is perpendicular to the loading direction, and this angle we have quantified it as theta. So what it essentially means is that this angle here is, so if you, the one that is notified by cross or one that is differentiated by cross is nothing but 90 minus theta. So what we are doing is, we are considering a triangle, say we will introduce a name for it. We are considering a triangle B and DE. We are considering considering a triangle BDE. So this angle here BDP, so this angle here is 90 degrees, so that means this angle also is 90 degrees, and this angle is theta. So therefore, since theta plus 90 degrees and this angle that has been mentioned as x should be equal to 180 degrees. So this sum of all these should be 180 degrees. What we would end up having is x is nothing but 90 minus theta. So this x is 90 minus theta. But when you consider the x, this x is a portion of this 90 minus theta. This x is the portion of the angle BE, and so this x is the portion of, so if you consider a point, say here F, so this point F here, this x is a portion of BEF. So x is a portion of BEF. But we already know that this angle BEF is 90 degrees. The angle BEF is 90 degrees. How do we know that? Because EF is nothing but the normal to BE. So therefore, so B in this E and F, this EF, the one in red, is nothing but the normal to AB. So therefore, BEF is 90 degrees. And we found that the value of x is 90 minus theta. So x plus the angle that we are interested in, the one that we have highlighted here, so let us call that x prime, is 90 degrees. So x plus x prime is 90 degrees. So this x is 90 minus theta plus x prime is 90 degrees. So we have substituted this relation here, and now this gets cancelled, and ultimately the x prime, the one that is in green, is nothing but theta. So this angle here is theta. So what we have identified is the normal of our region of interest is inclined to the loading direction, and the amount of inclination is equal to how much the overall region of interest is inclined to the BC, that is the cross-sectional area. So the overall region of interest, so if you replot it, what we would end up observing, if you replot the setup that we have been considering so far, we have an inclined region of interest, and this inclined region of interest, when compared to the perpendicular cross-section area, it is inclined by an angle of theta. Now when you consider the loading direction, so when you consider the loading direction, now the normal of the inclined, so the normal of the inclined region of interest AB is also inclined by an angle theta. So the angle between the loading direction and the normal of our region of interest AB is also theta. Now, having understood or having quantified the angle between the normal of the inclined region of interest and the loading direction, it is possible for us to understand what portion of the load along this, or the region of interest, experiences along the normal direction. Let me repeat, we are imposing the load along the longitudinal axis of the entire sample. So along this direction we are imposing the load P. Now we were able to introduce a new direction, that is a direction normal to AB. Now having introduced this direction, and in addition to that, having quantified the angle between the loading direction and the normal to our region of interest, it is possible for us to quantify what would be the load along this normal. What would be the load the region of interest experiences along this normal? But if you ask the question why it is important for us to rather quantify the load along this normal direction, because it is along this direction you would be able to understand the resistance offered by the atoms. So when you are able to quantify the load along this direction here, when you are able to rather quantify the stress along this normal direction here, it would be rather straightforward for us to relate to the resistance offered by the atoms in this normal direction. So that's the reason it is also necessary for us to consider the normal to the region of interest. So now what we essentially have is, we have two directions. We have load experience, load acting in the specific direction, and we have a normal direction. Now when we want to rather understand what is the load experienced in this direction, all we need to do is project the load experienced by our region of interest AB on to this direction here. So we need to project the stress experienced by our region of interest AB onto this direction here, onto this normal direction here. Now the stress experienced by AB, we refer to it as this. So this we derived in few minutes earlier, we derived this expression, that is the stress experienced by the region of interest AB is this. Now this stress AB is along this direction, that is highlighted in red. The stress AB is along this direction, that is rather highlighted in black. Now our interest is to find the stress along the normal. So we want to move from stress along the loading direction, stress experienced by AB along the loading direction, to the stress experienced by AB along the normal. So let us use a cap here. So we want to differentiate ourselves from the stress experienced by AB along the loading direction from the stress experienced by AB in the normal direction. Now, like I said, we know already the angle separating these two directions. So the stress here, it is along the direction of P, and this is along the normal direction. We have a magnitude, there is a definite stress associated along the direction of P, and there is a definite stress that we want to calculate along the normal direction. So what we essentially have is, we have a magnitude and we have a direction. So it means we are talking about set of vectors. So when we want to know what is the load acting along this direction, all we need to do is project this onto this, project this vector, the stress that is acting along P onto this, and this can be done by considering just multiplying the stress along this direction with cos of the angle that separates these two directions. So we have the direction P and we have the normal direction of the normal to AB, and it is separated, or it is inclined by angle theta. So when you want to project this onto, when you want to project the stress experience along P onto that of AB, the normal to AB, all you need to do is multiply by cos theta. So the stress along the normal direction to AB is nothing but the product of the stress along the P direction and the cos theta. So you are projecting the stress onto the normal. So you are projecting the stress onto our direction of interest or onto the normal direction of that of AB. So we arrive at this expression here, but we already have an expression for the stress experienced by AB along the loading direction P. So that is nothing but the sigma cos theta. So we can substitute this expression here, and what we would end up having is sigma cos square theta is what is the stress experienced by the inclined area of interest along the loading direction. So we have an expression for the stress experienced by our region of interest along the normal direction, that is N, is sigma cos square theta. So what we have essentially done in this lecture, to cap it all off, so what we have essentially done in this lecture is, we have considered an actual condition using the frame of reference. Instead of having an inclined loading direction, what we have considered is an inclined plane of interest. We saw that this inclined plane of interest, when the loading condition is rather the ones that we have considered in the test condition, in that case the inclined region of interest, the stress experienced by it is a portion of the stress experienced by the actual cross-sectional area. The inclined area of interest, it experiences stress that is a portion of the actual cross-sectional area, and this relation helps us understand what is the stress experienced by the inclined region of interest. When you consider the direction of the stress here, it is still along the loading direction. So this stress experienced by the inclined region of interest is still along the loading direction. Now when you want to consider the normal to our region of interest, when you want to change everything and talk in terms of our region of interest alone, we consider the normal to our region of interest, and when you do that, we end up with an expression of this form. So this stress is oriented towards the loading direction P, and this stress is oriented towards the normal to of AB. So this quantitatively, or this exclusively describes the stress experienced with respect to the inclined direction, particularly along the normal to that of the inclined region of interest. So with this, we will wind this lecture up and we will build on this understanding in the subsequent lectures. Goodbye.